Okay, so this is our second practice problem. We're redoing that first example that we had with sample sizes of 20. So remember, we had a sampling mean of 100 because our population mean was 100 and our population standard deviation was 15. So our sampling standard deviation, or the standard error of the mean, is the population standard deviation divided by the square root of the sample size, which in this case is 15. And now it's divided by the square root of 20, which is approximately, grab the calculator, 15 divided by square root of 20, 3.35. So 3.35. So let's draw our, and we're still looking for the probability of a mean greater than 110. Sorry, a sample mean. So that's terrible. Try this again. Okay, there is our curve. Our mean, remember, goes right in the middle, so 100. Our standard deviation is 3.35. So we subtract 3.35 going left from the mean, and we add 3.35 going right from the mean. So going to the right, we have 103.35. Then we have 106.7. And the third one is 110.05. Going the other direction, we have 96.65, 93.3, and 89.95. Now remember, we want greater than 110, so 110 is, I don't know, somewhere about there maybe. And we need greater, so that's to the right. So how do we find the probability? Well, the probability that the sample mean is greater than 110 is normal CDF again. And our boundary should be the same as the previous example. So the left boundary, the lower boundary is 110. The upper boundary is a bunch of 9s. The mean is still 100. This time the standard deviation is 15 over the square root of 20. So if we plug that in the calculator, we get 0.0014. So if you noticed, that is a smaller probability for the same thing than what we got in the previous problem. Our probability was 0.0175. Now it's 0.0014. It's a smaller probability because as our sample size increases, our spread, or the standard error of the mean, decreases. So if you see in this problem, our standard error of the mean was 3.35, with a sample size of 20, but when we had a sample size of 10, our standard error of the mean was 4.7. So if we have to interpret this, we can say exactly the same as before. The probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is 0.0014. So this time we'll say if we take 1,000 simple random samples of size n equals 20 individuals from the population, and I should really say from this population, and if the population mean is 100, about one sample will result in a mean IQ greater than 110. So this time, why did we choose to take 1,000 simple random samples? Well, if we look at the probability, the first non-zero digit is in the thousandths place. So to get our number of one sample, we're still doing probability times the number of samples, which in this case is 0.0014 times 1,000, which is 1.4, or approximately one sample. Now, as I pointed out, the first example, we had a sample size of 10. The second example, we had a sample size of 20. So how does the increase in sample size change the mean and the standard error of the mean of the from the sampling distribution? Well, changing n does not change the mean of the sampling distribution of the mean. But increasing the sample size decreases the standard error of the mean. And vice versa, decreasing sample size will increase the standard error of the mean. Okay, so that is how we do these problems if the original population is normally distributed. In the next video, we'll talk about what to do if the original population is not normally distributed.